Hello people and welcome to another video of Programmer's Corner. In this video we'll talk about how to find whether a given pattern exists in a given string. So as last time where we used Robin Karp to find that whether a given pattern existed into a given string, in this video we'll look at how to do the same thing using a deterministic finite automatons. So before we start, let me give you a quick overview of what a deterministic finite automaton is. A finite automaton is a state transition machine used to recognize patterns on a given string. So in this example, this is the given string and we are going to build a finite automaton which will recognize these two patterns and see if they exist and at what position each of the occurrence is. So the starting index of each occurrence. Now there are two types of deterministic and finite. There are two types of finite automatons. One is deterministic and the other one is non-deterministic. So before we get into the example, let me give you a quick view of what a deterministic and a non-deterministic finite automaton is. So a non-deterministic finite automaton is a state machine where you can go from one state to the other state, or you can go from one state to two separate states on a single input, on a single input. So like I can go from state S to state S1 on A, or I can go from state S to state S2 on A. So the machine here cannot determine which state to choose, since there is no specific direction of which state to go to. So this is a good example of a non-deterministic machine. A deterministic machine, on the other hand, specifies which state to go to. So in this case, if I find a symbol A, I know that the machine should go from state S to state S1. If I find a symbol B, machine should go from state S to state S2, so on and so forth. If I turn this to A, I can turn this machine into a non-deterministic finite machine. So in this example, in our example, we are going to build a string recognition machine using a deterministic model. So let's begin. For this example, I have created these two classes, the DFA and the DFA1 and DFA2, and I'm going to use something called the enum, which is basically a constant. Each of these have a constant, so this basically has a value of 0, 1 and 2 and so on and so forth. So initially what we did was, we have this string and we have to find that whether how many times does this pattern exist in the string or occurs in the string, and how many times does this pattern occurs in the string. One of the things about DFA is that I have to create a machine for this given pattern. I basically have to create a machine for this given pattern. So if you look at BC, I have created the DFA is a machine for BC. So before I go here, let me give you a quick overview of what I'm saying. So this is the machine for BC. So I'm at state S. I start with this current state and I go to state S1 once I find the symbol B in the big string, and immediately after that, if I find the symbol C, I go to S2. Otherwise I just stay in the state if I find the symbol B. If I find any other symbol, I go back to state S, because I want to find the pattern BC. I don't want any other symbols to be within B or C, or any other symbols that separate B or C. That's one thing. Now there is one more thing that we have to take into consideration, is that every transition machine has an initial state and a final state. In our case, once we find the C, we go to a final state, and once we go here, we print the first index of this pattern occurrence, or the starting index. So the index of B, that's what of the big input string that we have here, is going to be printed. So this is a pattern for C. But once we reach the final state, we are still not done with the string. So what if after that we again find the B? So we go back to this position, or if we find some other symbol, we go back to the start position. So this is what a deterministic machine is. So at every state it clearly states on what symbol what should be the next function or what should be the next state to visit. The second pattern that we are looking at is this pattern ACBDC. For this I'm going to check it against this and this string, and then I'm going to check it against this string. So both of these are being checked against two different strings. So this is our input into the machine. So let's see the automaton for this pattern. So this is the automaton for this pattern. This is my final state, this is my initial state. So the pattern goes like ACBDA, stated here. Sorry, ACBDC. Actually, I made a mistake here by typing. So this is the pattern that I'm going to check. So this is the pattern that I'm going to check, and let's see how the DFA is structured on this. So one of the things that you should see here is that each DFA is structured on the pattern that we want to check. So on state S, once we see A, we go to the next state. The next symbol, if we see B, we go to the next state. The next symbol is C, D, and A again. Once we hit the final state, we display the first index of its occurrence. Now the actual DFAs do not do that. They actually print whether the pattern exists or it doesn't exist. So if the output is 0, the pattern exists. If the output is 1, sorry, if it's 0, the pattern doesn't exist. If the output is 1, the pattern exists. So given that, let's see what are these other lines that we are marking on. We have S to S1, but let's say at A we find something other than C. So we go back to A because we have a break in the pattern. We have a break in the input string. That's not the pattern that we are looking for. After A C should immediately occur. So that's what happens. If we find C, we go to S2. But then again, at S2, if we have, now there is a catch here. If we have something like A, we might probably have a repetition of AC, A, C, B, D, A. This might occur. So if you take that into consideration. But if we find some other symbol, for example, D or any other random symbol, we go back to the start position because we don't have the pattern that we're looking for. There is no point in going to some other state. Once we find B, I come back here, but the same thing goes again. Let's say we have A, C, B, but instead of finding B or any other pattern, we find A. Well, we might have a repetition of the same thing. As I said for the previous state, we might have A, C, B, A, C, B, D, A. So that might actually send, so if we find A, we go back to state 1, but if we find some other pattern, we move back to state S. That's the start state. So we move back to the start state. Now, so this actually should have this. So this actually should have something along those lines. So this should again go back to the first thing on pattern, anything other than these three, anything other than B, or it should go back to the start state. But let's say we find D, so we go to D, so we go to state 4, and then we go to state 4, and then we see that from here, if I find any other pattern, I again go to the start, because I cannot have something along the lines of A, C, B, D, and if I find B again, I cannot go back because I want to see an A. I don't want to see B I don't want to see B again. So if I find B, I go back here, and if I find B, I go to this state, the start state. But what if I find A? If I find A, that we have found a pattern, we go to the final state, we print the output, or we submit the start index of the pattern where it's found in the big string, and we wait because the string is not yet done. The big string that we are traversing is not yet done. So what we do is, from here we then moved on to, we see what symbol we find next. If we find anything other than C, we go to the start state. But we find C, we know that there might be an overlap in pattern. We might have something like A, C, B, D, A, C, B, D, A. This can happen because I have made a test case of that, and in that case, if the pattern overlaps, we consider it, because now they have two patterns which are overlapping on each other. So we go back to state 2, because the state 2 is visited only when we find a C from its previous state. So given this is our DFA for this pattern. So as you can see, for the previous pattern we had a small DFA which was like 3 states, or including the start state and the final state, and for this pattern we have around 6 states including the start and final state. So in DFA string matching, each DFA is designed based on the pattern that you want to find in a given input. So let's go to let's see how the code is written. For the first DFA, which is this for pattern BC, I have created a function called indices, which returns the array list of integers, which stores all the string indices, which store all the indices of the first index of the occurrence. So what it does is it reverses to the output, it reverses to the input, and it sees which state it currently is in. If it's the start state and it finds B, I move the state to state 1. As you can see here, if I find B, I go to state 1. If I find C, I go to state 2. When I'm on state 1, if I find C, I go to state 2 and I add it to the output. Now I-1 is, the -1 is the size, the length of the pattern minus 1, because remember we start from 0. So in this case it will be 0 and 1. So we only want to shift one index behind. But if we don't find B, then we move to the start state. In addition, the same thing goes for state 2. If we are in state 2 and if we find B, so if we are in state 2 and if we find B, we go back to state 1, because we might have BC and then again BC. So we might have a repetition of, we might have like patterns next to each other. So if we find B, we go back to state 1 to see if the next pattern is C. If we don't find B, then we go back to the start state because we have a break in the pattern. And the end, we return the output of, which is the array list. The same thing goes for the integer, same thing goes for the DFA2 for the other pattern, the pattern of ACBDA. So in this case I have around 6 states, and the initial start is the same, where we return the array list, and we have the states, which the initial state is declared to be the start state, which reverses through the entire input, checking each and every symbol, each and every character from the input string. And in the initial stage, if we see A at the beginning, we go to the next state, so on and so forth. So when we are on state 1, when we are on this state, we basically see if we find C, I go to the next state. If I find something else, I go back. I don't stay there. If I find A in this one, I just keep on looping. If it's not A, I just go back. If it's A, then I just don't do anything, and I just go to the next character, because A and then C is still within the pattern range, or it hasn't violated anything. Once I go to state 2, as stated here, from here on A I go back to I go back to S1. On B I go back to S3. On anything else I go back to S. So on A I go back to state 1. On B I go back to state 3. Else I go back to start. When I'm on state 3, On A I go back to state 1, on D I go back to state 4, and else I go back to the start state. So on A state 1, D state 2, else I go back to the start state because the pattern has been broken and we want to start over again. When we go to state 4, I can see that I find an A, so I hit the state phi, I put the first index of this occurrent occurrence into the output. Now again, the -4 is because the pattern length is 5, and since we start from 0, we have to offset that by 1. So we start from 4, the length of the pattern, that's 5 minus 1, which is 4. Or if it's not A and it's something else, and we have a break in the pattern and we go back to the start of the loop. Now, this is what I'm talking about. This is what I was saying about. Since we haven't reached the end of the string, when I'm here and if I see a C, then I can see that from A there is a C, so it might be something, I don't know what the future letters are going to be, but then I assume that it might be the same pattern repeated which has been overlapped. So I have A, C, and if I see a C, instead of going here, I'm directly going to go here because I assume that there is a overlap pattern. If I don't find the same letter, if I don't find B, if I find something else, I'll eventually go back at the start position. So that's what I do. If I find the C, I go to state 2, else I go to the start position. And at state 2, as we stated above, if you don't find any of these two, I go back to the start. So this is and at the end of it, we again return the output of all the first occurrence of each indexes, or each index first occurrence. So this is the example for both the DFS. So let's run and see how it works. So as you can see here, for this given input, I see that BC occurs at the first index, it occurs at the 7th index, and it occurs at the 10th index. This thing, on the other hand, does not occur at all in this, so we have returned an empty list. BC with the second occurrence, the second DFA, occurs at 3 and 15. So it occurs at here, and then it occurs at the end of it. So this puts 3 and 15 in there. ACBDA actually occurs at 5 and 9, so there is an overlap here. As I was saying, ACBDA and then there is ACBDA, so there is an overlap of this pattern, and thus is gonna take this into consideration. So there is one more thing that I would like to add in this, which is something that I actually forgot to add, and that is, once we are at the last state, and if we see an A here, then what do you think, which state we should go to? So in this case, if we see an A, I'm definitely going to go to the S1 state, because that state is visited only when the symbol read by the previous state is A. So in this case, if we have something along A and then instead of C we again have an A and then a C, then we don't want to miss this part. The initial state actually missed it, so let's do state 1. So we again go back to state 1, and then if we see a C there, I visit state C, I visit to C, and so on and so forth. So this is the DFA for the second pattern, which is ACBDA. So if I run this again, in this case it's going to work because I did not write that, but if I change the pattern here, ACBDA, and then if I put an A here again, this time it's going to work again. So see, it basically worked. So that was the entire process. That was the entire algorithm for DFA, how to create DFAs using patterns. One of the plus things about this algorithm is the whole process. You have to only traverse the entire input once, so it's O of n being the size of the input. But one of the negative aspects about this is that it creates a question of how would you decide which pattern to pick given a string. So that's one thing that you don't know about, like people think about when you're using DFAs for pattern recognition, because you don't know what input is going to be in there, and so it's, even though it's efficient in traversing the whole thing, it's just O of n, it's still the choosing of each pattern. That's what's is the question in pattern recognition. So if you like this video, please comment, share, subscribe, and see you next time. Thank you.